right, so we're on lab number 7. Which is today's lab is magnetic induction and transformers. The first concept we have to go over is magnetic flux. So this symbol here is capital Phi. I put a little B on here so it reminds you it's magnetic flux. There's also electric flux, but today we're concerned with magnetism. And it's defined as B, which is the magnetic field times the area and the cosine of the angle between the two. Sometimes written with a dot product. So here I have a loop of wire that I put in a square, so it has a certain area called A. And then I have some B field into the loop with a certain strength B. So is there a magnetic flux in this loop? What do you think? Yeah, there is, right? Because we got a B field, we have an area, B times A, and what's the angle between B and A here? It's 90 degrees, so you do it with the plane of the area. B field's this way. Is that right? No. Well, okay, so the plane, you do like a vector away from the plane. That's the way they do it. So actually, it's cosine of 0, which is 1. Most of the time, you'll pick it 90 perpendicular to each other in such a way that this cosine will be 1. I know it's a little bit confusing. I confused myself. But that's flux. And the next concept we need to talk about is electromotive force. Sometimes it's written as EMF for electromotive force, or this little symbol here. Its units are volts, so it's actually a voltage. So it's kind of a misnomer. It's not a force, right? It's a voltage.
What's that in?
Oh, that's just the parentheses around my V.
Oh.
That's a V. Is that better? Any questions so far? All right, so now we can get to Faraday's law now that we define these things. So Faraday's law says a change in magnetic flux induces an EMF, which drives a current, and that creates a magnetic field which opposes the change in flux. So that's a lot of words, but after you play around with it a little bit, I think it makes sense. So over here we define flux. So if you have a changing flux, it'll induce an EMF, which is a voltage, right? So what do voltages do? They drive current, right? So it drives a current, and then that current is in a direction such that it opposes the change in flux. So that current is going to create its own B field, which opposes the change. All right. And so if we write that as an equation, we write that the EMF is equal to, well, ignore the minus sign for a second, the change in flux over the time. So if you have a changing flux, produces an EMF, which is a voltage, that'll drive a current. And which direction does that current go in? The direction that opposes that change in flux. So that's that minus sign, is the opposes. Sometimes called Lenz's law. So when Faraday first discovered this, he didn't put the minus sign there. A little while afterwards, Lenz came along and said, you forgot the minus sign. And so some people call it Lenz's law. Any questions? Let's do some examples. Here I have a loop of wire. I'm going to have the B field going into the wire. And it's going to be increasing. So it's changing. It's increasing with time. And the question is which direction is the current going to go in? So is there a change in flux here? Yes, because it's increasing. Which direction is the change in? Into the board. All right, so if the change in flux is into the board, we need to create a magnetic field from the current which opposes that change. So we need to create a current that creates a B field out of the board. And so the current would be this way. All right, let's do another one. So now I'm going to have the B field into the board, but decreasing. So we have B field into the board. Which way is the change in flux? It's decreasing, right? So the change in flux, it's getting smaller and smaller and smaller. The change is in this direction. Does that make sense? So the B field's into the board, but the change is out of the board. We care about the change in flux. The change in flux. All right? But we want to oppose that change. So we want to create a current that creates a B field into the board. And so we want to go this way by the right-hand rule, which is the opposite of this guy. So one thing I want to point out is it doesn't matter, I mean it does matter, but what's important is the change in flux, not the direction of the B field, right? Because both these B fields are in the same direction, but one's increasing and one's decreasing. It's the change in flux. All right, you want to do one more? Let's do a B field that's out of the board. Increasing or decreasing? What do you guys want to do? Increasing? I heard increasing. So it's increasing. All right, so we got a B field that's out of the board, and the change, it's increasing, so the change in flux is this way. But we want to oppose that change. So we want to drive a current which creates a B field in this direction. And we get, starting to make sense? All right, there's only one left, so we might as well do it, right? So we got a B field out of the board, and it's decreasing in time. So B field's out of the board, but the change in flux is into the board, and we want to oppose that change, so we're going to make a current that comes out of the board, and we got this way, right? All right, that's Faraday's law, Lenz's law. Not so bad, right?
If the magnetic field pivots, but the wire is fixed, is only the portion that is a projection?
Yeah, so then we have to worry about this cosine, right?
Yeah.
So the question is what if the B field's not, perpendicular to the area here, and then there'd be an angle there?
Is it only the projection that would affect the current, or is it more complicated?
It's the component that's in the direction, which is the same thing as taking cosine of the angle. All right, great. Transformers. What are transformers? Anyone know? Nobody knows what a transformer is? Everybody at once. Transformers? Robots, yes, from the movie. No, we're not talking about those type of transformers. All right, so a transformer is a way to step up the voltage or step down the voltage, or conversely, the current, step up the current or step down the current. And so we do that with some solenoids. So let's ignore this half for a moment, and just look at this solenoid. We've done solenoids before. If I drive if I put a voltage across here, we'll drive a current. Let's say it's driving a current in this direction. So if we're driving a current, what's going to happen inside the solenoid? What do solenoids have inside of them? Magnetic fields. So I'm going to draw it such that the magnetic field produced is pointing up. It's a B field. All right, so what if I drive alternating current through here? So that means the current's going to go one way and then back the other way, back and forth, back and forth, back and forth. What's going to happen to this B field inside the solenoid? It's going to go up and down, up and down, up and down. So it's going to point up, then it's going to point down, it's going to oscillate back and forth. All right, that's great. So now we have a changing B field. Now what we do is we put a piece of iron here, and iron is a high mu material. It likes magnetic fields in it, so it's going to keep the magnetic field sort of in the iron here and drive it around this loop of iron. All right, these aren't currents, these are B fields. So if these B fields are oscillating up and down, then these B fields must be oscillating up and down too. All right, if there's changing B fields here, is there a changing magnetic flux? Yes. And what does a changing magnetic flux do? Yeah, it produces an EMF in this wire. There's no battery in this wire, but now there's a voltage in it, an EMF, which is going to drive a current. Now, if this B field's changing back and forth, the EMF and the current is also going to be changing back and forth, so it's going to be oscillating too. But what's important here is that we produced an EMF and a current in this wire without a battery. So we took current and voltage from here, and we transferred that energy, that power, over to this loop here. And so if you measure the voltage here, you'll see a potential difference across the resistor. All right, and so the formula is, if you want to know what the voltage is in the secondary loop, you take the number of turns in the secondary loop divided by the number of turns in the primary loop, and then multiply it by the voltage in the primary. All right, so let's say there's 10 over here, 10 loops in the primary, and 20 loops in the secondary, and the voltage here is, I don't know, 1.5 volts. Let's do 2 volts. 2 volts. And the question is, what is the voltage in the secondary? So we can do that. We got 20 over 10 times 2 volts. So 2 times 2 is 4. So we expect 4 volts over here. 4 volts of alternating current. All right, so we increase the voltage. Does that violate conservation of energy? What do you think? No, it shouldn't, right? So voltage isn't the same thing as energy. So power is equal to IV. So here we stepped up the voltage, but you'll notice if P is constant, the power is constant, which is energy per unit time, then we had to step down the current. All right, why would you want to step down the current? Step up the voltage?
So you don't damage your sensitive electronics.
Right, so you don't damage your sensitive electronics. So if you produce a lot of power at some power station and you want to send it some distance, so outside of Portland there's some power plant miles away, and they have to send that power to Portland. Now, do you want to do that at high current or low current? Why high? I'd want to do it at low current. And that's because the higher the current, the hotter the wire, right? We know that. We played around with current in here. The wires get hot. And that means energy is being lost. And since we sell that energy, right, the power plant sells that energy, they don't want to lose it. So they step up the voltage and they step down the current. And when they get back to Portland, they send it through a transformer and they step up the current, step down the voltage. Any questions on transformers? So what do transformers do? Step up or step down the voltage or current. All right, and so I just want to emphasize that out of all the laws you probably learned, Faraday's has probably impacted your life the most. And that's because this is how all power is generated. Okay? There were batteries, right? But batteries are kind of limited in how much power you can produce with a battery. They're chemical. But you can take something that moves something, so your turbine, right? So you can heat up water with coal or oil, spins a turbine. You hook that turbine up to some coils of some magnets with some coils around them. And that induces an EMF in the, so this is sort of how all power is generated. And so out of all the laws you've learned, you know, there's been what, Gauss's law, Ampere's law. This one's probably impacted your life the most. And so there's like an old story. When Faraday discovered this, he went out and he showed people experiments and, you know, say, look how cool this is. And there was a mayor in London who was like, yeah, okay, what's so great about that? You know, it's just like little tricks. And Faraday said, well, what's so great about it? Someday you'll be taxing it. So Faraday knew how important this was even before people of his time. Any questions? All right, I want to demo this real quick.